Hi, good morning, everyone. So during last session, in last two sessions, we have completed the number, how to calculate the number of atoms, and then the introduction of about solid state. And now today in this class, we will see close packing of unit cell, right? So how the atoms, I mean the constituent particles, are arranged in 1D and 2D that we will see today. In one dimension and in two dimension, we are going to see in this class, during this class, about the close packing of unit cell. So before going to directly to the close packing of unit cell, so let me introduce a term that is called a coordination number. Right? This is very important. Coordination number. So the coordination number in particularly in the solid state, what we can say is, see, if I consider these three or just atoms, I mean the constituent particle, then if you consider any atom, right? If you consider any atom, let us consider this one as a particular atom or constituent particle. So the number of neighboring atoms directly attached to a particular atom is called as coordination number. That means, see here, if I consider this atom as a particular atom, then to this atom there are two, atoms, I mean constituent particles are in direct link. So that means here, in this case, what is the coordination number? 1 and 2, right? So likewise, the coordination number is nothing but the the number of neighboring atoms attached to a particular atom. That means the number of neighboring atoms attached to a particular atom is called as coordination number. So the coordination number does changes in case of different arrangements. So this is one, we can say one dimension, we can say, right? So that means here, what is the coordination number? 4. Likewise, we will see the coordination, different coordination number in different, I mean, arrangements, right? So coordination number is nothing but the number of neighboring atom directly attached to a particular atom is called as coordination number. So that means the coordination number changes or varies with the different arrangements. So in one dimension, one we can see that the number of neighboring atom, I mean the coordination number will be 2. If the arrangement is like 2D, we will see later, we will see during this class. In 2D, in two dimension, one we can write two type of arrangements. So that is A type, and one more AB type, right? So in A type, we will going to see the coordination number is 4, and in AB type the coordination number will be 6. But in 1D, if I arrange the atoms in a 1D, then the coordination number, one we can see very easily, there are 2. So again, we will go in detail about this. That means the coordination number is very important now. So the number of neighboring atom has direct link with the particular atom is called as a coordination number. So first we will see close packing in one dimension, right? So in close packing in one dimension, we will going to see what type of arrangement and the number of I mean what is the coordination number, one we can see in case of one dimension. Close packing in one dimension, right? 1D, right? So one dimension is nothing but one we can see a one quantity, right? So that might be a length or might be a breadth, right, or height. So that means, see, if I arrange the solid particles or the solid constituent particle in one dimension, then they looks like this, right? Just now we had a diagram now, like the same thing will appear here. Why? Because one dimension means we can arrange these atoms in only one row. So that is very important. So one dimension in solid or the constituent particle, when we can arrange in only one row. So now what is very important for you people to remember here is what is the coordination number, right? They may directly ask during your I mean this part is very important for your competitive exams, right? So in that case they might directly ask what is the coordination number in one dimension type of arrangement, right? So in that case, as I said, you consider any in between atom. That means it is not the end of this solid, it is the continuation. The n number of constituent particles are present in this solid, we know that and that means if I consider any atom, you can consider this or this, any atom you can consider. If I consider this constituent particle, then in one dimension there are two constituent particles are in direct link. So that means the coordination number of 1D will be equal to 2, right? So always in one dimension or one dimension type of arrangement, one we can see that two, I mean the coordination number will be always 2. Why? Because in one dimension we can arrange the constituent particle in one row. So thus, if I consider any particular atom, then definitely here in 1D, we can see the two atoms will be always in the what direct link with the particular atom. So this is the case in close packing and in close packing in one dimension. So right, so this that means for one dimension the only one arrangement one we can see, right? So coming to 2D, two dimension arrangement here, like as I said before, in two dimension one we can see two different type of arrangements, right? So first we will see there are two type of arrangements. That means A type, right? One type, and one more is AB like this, right? You can take any XXX like this or YYY. You can abbreviate this with any alphabet, right? So there is no particular alphabet to represent A. There is no rule, right? So coming to AA type, that means the arrangement will be same type, right? See here. If I write the arrangement, that means 2D means we have to consider two quantities. A type means the next, I mean the next row will be same as first, right? Like this. A type, right? You can say one more, you can write one more row like this. Now you consider what is our main intention to check this is to count the number of constituent particle, means the coordination number. If I consider any atom, you can consider in the middle row. So that means you can very easily understand. So if we consider middle row atom as a particular atom, then to this atom you can see directly, see this atom is directly in link, right? You can clearly observe here. This one, this has no connection with this particular atom, so that's why leave that. And now, what about this? This is also in direct link, and this. That means here in AA type of arrangement, the coordination number will be what? 4, right? Clearly you can see. See, if I consider this atom as a particular atom, then to this atom there are 4 constituent particles are in direct link. So that's why in A type of arrangement the coordination number will be 4, right? So coming to one more type, that is AB type, right? So in AB type, so that means A is different, having different arrangement than B. So that's why we are using two letters A, B. The indication is A is having a little different arrangement as compared to B. So that is the intention why we are using two letters. The single letter, I mean the same letter is nothing but same arrangement. Right? So if we consider this, I mean second type of arrangement, then B will come middle, right? So that's why we are abbreviating like this. That means A is different than the B. A is totally different than the B. That means A will come at the middle. That is very important. So the B arrangement will come at the middle of A. So that's why the arrangement name will be different. So like this, right? You can see very clearly in your book. So I am trying to give a clear idea, but let us see we will get success or not, right? So consider any one middle atom. So that means, see here, if I say this as a A type of arrangement, then this arrangement is different. So that's why I can say this as a B. And this last row looks like A. So that's why AB type. You can have the number of rows, no problem. So now here, again, what we need to do is, we need to calculate what is the coordination number of the arrangement called AB type, right? So again, you consider any one atom. So to this atom, so directly we have 1, 2, 3, 4, 5 and 6. So that means like this, there are 6 atoms are in direct link with this middle atom. So that's why here we can say hexagonal type of arrangement, right? So in case of AA, we can see tetrahedral type of arrangement, but here one we can say hexagonal type of arrangement, and here the coordination number will be always 6. We can easily see here. That means to this center atom, there are 6 constituent particles are in direct link. So in 1D and 2D, we saw what type of, I mean the coordination number. So these are the very important for competitive examinations, and as well to understand these further concepts, whatever they come in this chapter. So these parts are very important, right? So let us move towards the very important part of this chapter, that is packing efficiency. So before going to packing efficiency, what I decided is, in today's class I will just give you what are the requirement to understand packing efficiency, right? So today we will discuss this, and in tomorrow's class we will go with the packing efficiency directly. So here we need to know what is edge length, right? And this is denoted by letter capital A, right? And what is edge length we will see later. And next one is radius, and this will be represented by small r, right? So we need to see these two things, right? So in our cube, I mean lattice. So consider a cube, a unit cell. In unit cell, what we all have, I mean, we have corners, right? And the faces, I mean walls. So how many corners? There are 8 corners. Again, the faces are 6, and then the center will be always 1, right? So the successful distance between any 2 corner atoms, right? Very important. A complete, or else you can say a complete distance between any 2 corner atoms. You can consider these corners, these 2 corners, or else you can just consider these two corners, or else you can consider these two corners all are same. That means the complete distance between any two corner atoms can be called as edge length, and which is represented by letter called A, right? I mean, here you can see clearly. So any distance, I mean successful distance between any two corner atoms, any two corner atom in the unit cell. You can say, you can consider these two corner atoms, or else downwards corner atoms, or the backside corner atoms. You can consider any corner atoms. The complete distance between the two corner atoms is called as edge length, and edge length will be represented by A, right? And half of the distance between, right? Half of the distance between any two constituent particles is called as radius, and which will be represented by small r, right? So the half of the distance is nothing but radius, and the complete distance between one corner atom to other corner atom will be called as what? Edge length. So dear students, today this is all about today's class. In the tomorrow's class, very important, tomorrow's class will be very important. So do attend those that class, or follow that class. In tomorrow's class, we will move with the very important part of this chapter, that is packing efficiency. Thank you.